And so, in order to discuss the electrical potential and the electric generated by these cells, we need to be familiar with some key terms involved in electrical measurements. And those key terms are going to be the electrical current, so the flow of those electrons in a given amount of time, which is measured in the units of amperes, which is a fundamental SI unit, so it can't be broken down into subunits. The electrical charge, which is Q, and it's either represented with a capital Q. Occasionally you'll see it also represented as a lowercase q. That's measured in the coulomb. It's called a coulomb. Just like coulombic interactions are the interactions between charges. Coulomb is the measured unit for charge, and that is the ampere second. So the electrical charge in amount of time. The electrical potential, so the difference in those electrical states, the difference in their potential to create extra electrons, is measured in the volt. The volt can be broken down in this idea that we're looking at how much power can this electrochemical cell, which is measured in watts, produce for the current being generated. Which is the same thing as saying, well, how much energy can we transfer in a given amount of time for the current that's being produced by our electrochemical cell. So this electrical potential really directly correlates to how much energy, how much power we're going to be able to generate. The battery inside of your car contains way different materials than the batteries that you use for your AA's. There's a much different electrical potential for AA batteries than there are for the battery in your car. The reason being, these batteries don't need to produce as much electricity as your car battery does. So the electrical potential between the terminals and the two half cells in the AA batteries that you're familiar with is about 1.5 volts. Does anyone know what the car battery voltage reading should be? It's much larger than that. It's about 12 volts if you have a standard sized car. If you have a large truck, it should be about 18 volts. So a much larger electrical potential because it can produce a higher amount of power. So it moves more charge with more energy in a given amount of time. Now, any system is going to have a resistance associated with it. So those electrons aren't free floating, running around through a vacuum. We're transferring them through a wire. There's going to be some impediment to their flow. That impediment is their resistance to flow. And that resistance is measured in what's called ohms. And that is a measure of the potential over the current flow that's being generated. So there is going to be some electrical potential lost as those electrons are flowing. How much energy do we spend in just getting those electrons to move through the cell? It's watts. It's a measure of power. So W represents watts, which is a measure of power, which again is how much energy is produced in a given amount of time, so a joule seconds. Of course, you need to be familiar with the concept of time. When we're talking about time in electrical terms, we are going to use the fundamental SI unit of seconds. And then frequency is really important because frequency relates to how quickly those electrons are transferring in an amount of time, which directly relates back to this idea of current being the flow of those electrons. That frequency is in hertz, which is the same thing as a reciprocal second, so 1/seconds. Current is the number of electrons, so the number of charged units that will flow through a system in a given second. 1 ampere of current is equal to 1 coulomb of charge flowing every second. And that coulomb of charge has associated with it a very specific number of electrons. That very specific number of electrons related to 1 coulomb of charge is related by what's called Faraday's constant. And for Faraday's constant, it tells us that there are 6.242 times 10 to the 18 electrons for every 1 coulomb of charge. I will double check and make sure, but I am fairly sure that Faraday's constant is one of the constants that is provided on your exam information sheet. So it is one of the ones that are provided. Thank you for checking. The movement of electrons follows the electromotive force. So the electrical potential. So just like using the flow of water from a higher location to a lower location to generate electricity through hydrodynamic power, you can think of the channeling of electrons from a higher electrical potential at the anode to the lower electrical potential cathode can be used to generate electrical power by that means. That movement from the higher to the lower region of electrical potential energy is the electromotive force. The more important term to grasp from this, though, is that electromotive force, that difference in that potential state, is your cell potential. This relates to how much power, how much energy can be produced. The larger the difference is from your anode and your cathodes, the greater the power produced from that cell can be. So the anode and cathode cell potential for our AA batteries is much smaller. The difference between the redox potential and the oxidation potential of the anode and cathode in our AA batteries is much smaller than the electrical potential of the anode and the cathode in our car battery. That's why our car battery could produce way more power than a AA battery. And that cell potential, again, is measured in volts. It's a measure of how much energy is transferred per coulomb of charge. To get the electrical potential for an entire cell, it's the reduction potential minus the oxidation potential. Okay. When you perform a reduction, there's this energy associated with it. The amount of energy that can be used of that association is however much wasn't needed to rip the electrons off from the first place. Which generates the question of, well, how do we know who is going to be our reduced species? Who do we know is going to be our oxidized species? How do we know that this is the anode? How do we know that this is the cathode? Which way are the electrons going to flow? What is their direction? They're going to always flow downhill. They are always going to flow from the species of higher electrical potential to the species of lower electrical potential. And so if we had two half-cell reactions, one of them looking at a zinc electrode in series with a hydrogen electrode, the zinc has a higher electrical potential. So the electrons are going to flow out of the zinc to the hydrogen. Cool, awesome. How did I know that zinc was higher electrical potential than hydrogen? It is a table, but it is not the periodic table. a lot of the standard potentials for most of your electrodes have already been measured for us, and they've been created into a very nice standard potential table. So the standard potentials that are listed in the table are for all of the half reactions for a lot of the standard electrodes, but they're all written as reductions. So keep that in mind. They're all written in the format of them gaining the electrons. So when we're looking at who's going to give up those electrons and who's going to gain those electrons, the species that has the lowest energy, so the most negative electrical potential for the reduction, the one that's going to gain those extra electrons, is going to be the one that loses it. The electrons will always flow to the more positive standard potential. It's easier for the more positive standard potential to gain electrons. That's why it's reduced. It's harder to add it to the one that doesn't want them. Now your book gives you this beautiful, teeny tiny, really hard to read table of all of these extra electrical potentials. Not a big fan. So if you're sitting back there squinting your eyes going, I can't read that, I can't either. The table that I prefer are these. I'm going to move them up here for you. It's a little better. But the idea is that the reduction potential for all of these reactions have already been calculated for you. All you need to do is be able to decipher what this table is telling you. And what this table is telling you is that if you have a higher compound on this table, so for example, hydrogen is here, whereas zinc is down here, the hydrogen is going to take the electrons from the zinc. That is all that this table is pretty much telling you. It's telling you that if you have two half cells and you look at those half cell reactions and you find them on here, the one that's higher is going to be the one that is reduced. It's the one that's going to gain the electrons, which means conversely, the one that's lower is going to be the one that's oxidized. So the one that's higher is getting reduced, which means it's the cathode. The ones that's lower is being oxidized, which means it's the anode in our galvanic cell. If you're familiar with the activity series, this is a very similar concept to the activity series, which is that metals with a higher activity, so that means they have a higher electrical potential, are going to take electrons away from metals that have a lower electrical potential. And you guys know that I like acronyms. I've created an acronym for some of the more common metals that you'll see in these galvanic cells. So if I had a galvanic cell that contained a potassium electrode and a calcium electrode, who is going to take the electrons? The higher one, so potassium, which means that potassium is going to be oxidized or reduced. It's going to be reduced, which means in the galvanic cell, it's going to be the cathode or the anode if it's being reduced. Cathode. Okay. Which means calcium, since it's losing electrons, is going to be oxidized or reduced? Oxidized. And since it's being oxidized, this is going to be the cathode or the anode in our galvanic cells. Good. If you're curious, the way that we got these standard reduction potentials is we've measured them. But we've measured them all to an arbitrary standard. So you'll notice in your table that the reduction of hydrogen has a potential of 0. That's not to say that there's not activity associated with that. We've just defined that as 0. So that's our relative starting point. And then all of the rest of these are measured relative to that reduction potential. And so the most common standard electrode, and there's a large series of standard electrodes, these are the ones that are commonly referred to as your reference electrodes a lot of times when you're doing these experiments, is the standard hydrogen electrode. So that way, when you are measuring a circuit with a standard hydrogen electrode, the reduction potential you read will directly match up with the chart. And so what they do to measure those reduction potentials is they set up the 2 half cells, one of them containing the standard hydrogen electrode, the other containing the half reaction of interest, and they measure the electrical potential that's created. That's how they created that table, so that you don't have to. But that also means there's a lot of really interesting information from that table that we can pull out based on those electrical potentials, based on their propensity for taking electrons or giving away electrons. We can determine who is the stronger oxidizing agent, who is the stronger reducing agent. Now remember, when it's followed by agent, it means it's causing it to happen. So if I say oxidizing agent, it's not the one that's undergoing oxidation. It's the other one. It's the one that's causing it to happen. So it's the one that's going to be reduced. Which means on our table, the higher the compound is, the stronger of an oxidizing agent it is, the more likely it's going to be reduced. The more likely it is going to steal the electrons, the higher it is on that table. Which conversely means the lower it is on that table, the stronger a reducing agent it is. The more likely it is to steal said electrons. This is another concept that I can guarantee is going to show up on your final. You may not be given the beautiful table. So look at your relative numbers. The more positive its reduction potential, the stronger oxidizing agent it is. The more negative the reduction potential, the stronger reducing agent it is. It may help to think of this in terms of if it's really negative, it really wants to be negative and steal those electrons. Which means it wants to cause, let me have it backwards, hold on. It's causing reduction, which means it's giving away its electrons, so it's unhappy in its negative state. Converse. So the more negative, the stronger reducing agent, the more likely it is going to cause reduction. So the more likely it wants to get rid of its electrons so it can be happy and more positive. You will be given numbers rather than a nice vertical table. So be able to recognize the trend of this, which is that it's going from more negative to more positive. So, that being said, if I gave you a series of electrodes, say I'm looking at lithium, sodium, and aluminum, which of those is going to be the strongest oxidizing agent? Which one's going to be the strongest reducing agent? Lithium. Good. Why? Good. Lithium has the most negative value. Aluminum has the highest value of those three. Good. Since we have these standard reduction potentials, that also means that we can calculate an actual numerical value for the standard cell potentials of two given half cells. And so for any galvanic cell, the standard cell potential is going to be the reduction potential of the oxidation reaction minus that of the oxidation reaction. Very good question. Yes, standard conditions are the ones that you're familiar with. So when we're talking about standard potential, we're talking about standard conditions being 25 degrees Celsius, 1 atmosphere of pressure, 1 molar solution concentrations. Something to note on this is if you have to multiply the half cell reactions in order to add them together to get the net overall reaction, unlike what we did for our equilibrium constants and things like that, or to enthalpies, you're not going to multiply your standard reduction potentials. All right, so don't do that. It's not a multiplicative property of the cell. I like to rewrite this equation like this to avoid the confusion of the fact that we are given in our table reduction potentials. And so when I see this equation written like this and I see E of oxidation being subtracted, I want to flip the reaction around and take the negative of that. Don't do it. What this equation is really telling you is that the standard potential of your electrochemical cell is the reduction potential listed in the table for your cathode, which of course is the one that's undergoing reduction, minus the standard potential that's listed in the table, don't do anything to it, for your anode. So the one that's undergoing oxidation. Don't change the values. That's the big takeaway. Don't change your electrochemical potential values. They're what they need to be. So don't multiply them by any coefficients. Don't change the sign on it if you have to rearrange it for the cell. They are what they need to be and they already fit into the equations. So for example, if I'm looking at the electrochemical cell of zinc and copper, the oxidation potential for this is the oxidation of our zinc, which from the table I find out has an electrical potential for that reduction reaction of minus 0.7 volts, and I leave that alone. For the reduction, which is the reduction of the copper, I find it has a reduction potential of plus 0.34 volts. So to get the electrical potential associated with this cell, I take the electrical potential for the reduction of my cathode, so where my reduction is occurring, minus the exact value listed on the table for that of my oxidized anode, which gives me an overall electrical potential of plus 1.0 volts. The other information that we can get from the table is whether or not we're looking at a cell that is going to be a spontaneous galvanic cell. So those electrons are going to flow as long as we hook everything up correctly. Or if we're looking at a non-spontaneous reaction. And so those electrons aren't going to flow without some outside input. And so predicting the spontaneity of redox reactions based on their standard electrochemical potentials is basically, if it's going to be spontaneous, the standard cell potential should end up being positive. Okay. We should be able to generate some power with those electrons flowing through. If it's going to be non-spontaneous, however, you're going to end up with a negative cell potential. Means we're going to have to put in some extra work to get those electrons to flow. It's not impossible for that reaction to happen. It just requires external driving forces. And so what that means is if we were to switch our electrodes around, we would be generating a non-spontaneous reaction. So with our copper and zinc, as long as the zinc is being oxidized and the copper is being reduced, the overall cell potential ends up being that 1.1 volts, which is positive, which is going to be spontaneous. If we go the other way around, which means we're switching who's the anode and who's the cathode, so copper being oxidized, making it the anode, is going to end up with a reduction potential of minus 0.34 when we fill it into the equation. And zinc being oxidized to zinc solid is going to end up being filled in as that minus 0.76 volts. So the E of our cell ends up being negative 0.76 volts minus 0.34 volts, which ends up being negative 1.1 volts, which is non-spontaneous. All right, so if you generate a negative E naught for your cell, it is non-spontaneous, which basically means that you are trying to replace a higher metal with a lower ion, which can't happen. So I would like for you to try that without me standing up here and walking you through it. So determine if this is going to be a spontaneous reaction. And if it's going to be a spontaneous reaction or not, I want you to determine the standard cell potential for the given galvanic cell shown there. So what did we determine? Is this going to be spontaneous or non-spontaneous? It's going to be spontaneous. Why? We have a higher compound being replaced by a lower compound. So our higher compound on our cell table is being replaced by a lower compound, so higher, lower. If we were to calculate the E of our cell for this, which is as we have it written here, we would find that we need to do the reduction potential for our cathode minus the reduction potential of our anode. Which one's our cathode, which one's our anode? Right? Because the anode is where oxidation occurs, and we say we write oxidation first. The cathode is where reduction occurs, and we write reduction after it. And so our cell potential ends up being 1.36 volts plus, well, minus a negative, which makes it positive, 1.66 volts. So what is our overall standard cell potential for this? Positive 3.02 volts, which means it is a spontaneous galvanic cell. It is going to create power in its electrical potential. If we're discussing spontaneity, that means we can also think about it in terms of Gibbs free energy and the equilibrium constant K. For a spontaneous reaction, what do we know about Gibbs free energy? What does it have to be, positive or negative? It has to be negative. For it to be spontaneous, our standard cell electrical potential has to be positive. And our equilibrium constant needs to be bigger than 1. If we put all of that information together in this nice trifecta, what we end up with is something that relates our Gibbs free energy to the electrochemical cell potential, which is the Nernst equation. And the Gibbs free energy for our electrochemical cells is equivalent to the negative of the number of electrons we're moving times Faraday's constant, which is given here in terms of coulombs per mole of electrons instead of just straight electrons, times your standard cell potential. Follow your units.
So are we given both of the constants on our sheet or just one of them?
You'll be given both if you need them both. You'll be given the one you need. Which means we can establish a relationship between our standard electrical potential and K. Because we know that delta G naught is equal to negative RT ln of K. We learned that in the previous chapters. We just talked about how delta G is equal to the negative in F E naught of the cell. Filling in that information and rearranging and substituting in that we're at standard potential for T, so 298.15, and replacing the natural log base E with log base 10, which is where the 0.592 volts comes from. Those two changes allows us to come up with a very useful equation for relating our standard cell potential to our equilibrium constant K. Which means we can also relate that standard cell potential when we're not at standard conditions, when we're not at equilibrium, when we're dealing with a reaction that is still working its way towards equilibrium. In other words, instead of K, we have the reaction quotient Q. When that's the case, if we fill in our information that we know for delta G, so Gibbs free energy when we're not at standard conditions, should equal the number of electrons times Faraday's constant times the non-standard electric cell potential, which should be equivalent to what we just said the standard cell potential is equal to, plus that RT ln of Q, not K this time. Taking out all of the like terms, we end up with the Nernst equation that allows us to calculate what our cell potential would be if we're at non-standard conditions. So if we're not working with concentrations that are 1 molar is the most common situation where you'll be looking at non-standard conditions, where your reactions aren't using electrolytes with 1 molar concentration. Should be given. You will need to understand what the Nernst equation is telling you. Since it's related to the reaction quotient Q, that means we can change our cell potential by changing the concentration of our compounds. And depending on how we change those concentrations, we can change what our cell potential is going to be. Remember, there's an inverse relationship between the log of a value and the value itself, which means as we increase Q, we're going to decrease the log of Q. Which means if we make a whole lot more products, so we add in extra products in our reaction, or take out reactants in our reaction, we're going to make the Q term smaller, which is going to make this subtraction term smaller, which means we're going to move closer to the normal standard cell potential. So far we've discussed only the spontaneous reactions. Only the ones that when we put everything together, we're going to get electrons moving around. But I've said we can have those non-spontaneous ones. We just have to introduce extra electrons from somewhere. Oftentimes the way we do that is we create a circuit, stick a battery into that circuit, and use the battery to force those electrons to flow. When that happens, you can force the reverse reaction. So if we wanted to look at a circuit where we reduced copper instead of zinc, we could make that happen by applying an external current. When we do that, we are driving a non-spontaneous reaction, and we are working in what's called an electrolytic cell at that point. In the electrolytic cell, a key thing that's different that I really want to strongly point out is that we change the signs associated with our anode and our cathodes.